All right, we are on the hunt of a derivative rule for every situation. And one way that we often put formulas together is by adding two pieces together. So we should probably come up with a derivative rule for a situation where we have a function that is a sum like this. Based on our experience with the constant multiple rule, probably we expect that the formula we get will involve some combination of the derivative of f and the derivative of g. So as we work this out, we'll have to keep ourselves on the lookout for limits that look like the derivative of f and the derivative of g. All right, so since we don't have a derivative rule yet, we have to write down the definition. So this is the limit, the definition of the derivative as a limit. So this is the limit as h goes to 0 of f plus g of x plus h. Now be careful here, this isn't multiplication, so don't go distributing this. This is a function evaluation. So f plus g of the x value x plus h minus the function f plus g of x all over h. So limit as h goes to 0. Well, what is f plus g of x plus h? That's f of x plus h plus g of x plus h. That's just what we mean by the sum of two functions, right? It's the function that you put the x value in and then you add the results. Okay, minus, and then over here, same thing. This is f of x plus g of x all over h. Now remember, we're kind of expecting the derivative of f and the derivative of g to show up in some way, and there are some pieces for the limit that will give us the derivative of f and the derivative of g. These two pieces are things that we need for the derivative of f, so let's group those two pieces together. So limit as h goes to 0 of f of x plus h minus f of x. In fact, we can break those off into a numerator on their own, plus, and then we can group the pieces that have the g's. So this is the g of x plus h minus g of x over h, right? So we're taking the limit of this whole thing. But we can use the sum rule for limits, right? As long as the limit of each piece separately exists, it's okay to take the limit of each piece. So limit as h goes to 0 of f of x plus h minus f of x over h plus the limit as h goes to 0 of g of x plus h minus g of x. Out of room there. Okay, now this first piece, right, I hope you're keeping your eyes out for the derivative of f and the derivative of g because they're staring us in the face. This first piece, that is the derivative of f. That's just the definition of the derivative of f at x. And the second piece is the definition of the derivative of g. So this gives us a derivative rule for the derivative of a sum. The derivative of a sum is the sum of the individual derivatives, right? I guess the Leibniz way of writing this would be that d dx of f plus g is df dx plus dg dx. All right, so this is the sum rule for derivatives, which again, this sum rule turns out to be pretty much what you would expect. To take the derivative of a sum, you just take the derivative of each piece separately and then add them together. So that's the sum rule. How does it work for differences? So what if it were subtraction instead of addition? Well, I mean, if we had a minus here, that would just make us put a minus here and here, and then we'd have a minus here and here, and then that would make this a minus, and that would make this a minus, and that would make this a minus, and so we'd have a minus right here, right? So The short version for differences is if it's a difference instead of a sum, you just get a difference over here, which again is what you would expect, right? If you're going to guess what the sum rule should be or the difference rule should be, that's what you'd guess. So let's look at some examples. Now, one really nice thing about having the power rule, the sum rule, and the constant multiple rule is that we now have the ability to find the derivative of any polynomial without having to take any limits. Since polynomials are just made up of terms with exponents, constant multiples, and sums and differences. So let's use these derivative rules to take the derivative of x cubed minus 5x squared plus 3x minus 2. Now you can imagine doing this, finding this derivative using the limit definition. It would take a whole bunch of algebra. But what we'll do instead is break this up across the sums and differences using the sum and difference rule. So this is the derivative of x cubed minus the derivative of 5x squared plus the derivative of 3x minus the derivative of 2. Okay, for this first piece, use the power rule. The 3 comes down, x, and then the power decreases by 1, so x squared minus. Now we can use the constant multiple rule, right? The constant multiple rule says just move that 5 out in front, and then take the derivative of the stuff that's left over. And the derivative of x squared is 2x to the, 2 minus 1 is first power, plus, now for this term, 3x, again, we can move the 3 outside the derivative, and then take the derivative of x. Well, x is x to the first, so the derivative of x to the first is that 1 comes down, and then times x to the 0, right? Minus, and then what's the derivative of 2? Well, 2 is a constant, and remember the derivative of any constant is 0. Okay, and then we can clean this up a little bit, so 3x squared minus 5 times 2 is 10, x to the first, that's just x, plus 3 times 1 is 3, and x to the 0 is 1, so it's just 3. All right, so you can see we found this derivative in just a little bit of calculation, and once you get a little practice, you won't even need to write down these intermediate steps. You'll be able to jump directly to the answer once you have some practice. So, until you're sure that you've got it, do write out all of this work just to make sure you aren't missing any steps. All right, for a second example, let's calculate this derivative. So derivative of the square root of x minus 1 over the square root of x. We can calculate this derivative just with the derivative rules we have, because the square root of x is x to the 1/2, and 1 over the square root of x is x to the minus 1/2. So we can just use the difference rule. So we need the derivative with respect to x of x to the 1/2 minus the derivative of x to the minus 1/2, and then we can use the power rule. So the 1/2 comes down, times x to the, and then 1/2 minus 1 is minus 1/2, minus, and then use the power rule over here. The minus 1/2 comes down, times x to the, and then this exponent here should be minus 1/2 minus 1, so that's minus 3/2. And then, how we write this is sort of up to us. Whoops, sorry. So we could write this as 1 over 2 square root x, and then plus, I guess, 1 over 2 times x times square root of x. Okay. Maybe what we could do with this example, just to see that these derivative rules really are giving us correct results, let's compare the graph of our original function and its derivative, just to see that the graph of the derivative looks like it's the graph of the derivative. So for f of x, that's the square root of x minus 1 over the square root of x. And ends up looking kind of like a log, but it's not a logarithm. And for our derivative, so I'll call it g of x, but keep in mind that it's really the derivative. We get 1 over 2 times the square root of x plus 1 over 2 times x times the square root of x. Okay. Now this looks right because here where the original function is going up steeply, its derivative should be large and positive, and the g function is large and positive. Now as the function f, as we move to the right, it's the slope of its tangent lines stay positive, but they become small and positive, and the derivative function g does become small and positive as we move to the right. So maybe that convinces us a little bit that all this machinery that we've come up with to calculate derivatives really is still giving us the same old slope of a tangent line that we originally wanted it to. For one more example, let's suppose that an object is dropped from the top of a building so that its height above the ground in meters after t seconds is given by this formula. Let's find the velocity of the object after t seconds. So remember that the velocity is just the derivative of position. So we need to take the derivative with respect to time of our height function. So this is the derivative of minus 4.9 t squared plus 50. Now we can use the sum rule. So this is the derivative with respect to t of minus 4.9 t squared plus the derivative with respect to t of 50. Well, the derivative of a constant is 0, so this part is 0. In this first piece, this minus 4.9, it's minus 4.9 times t squared. So we can move the 4.9 outside of the derivative. That's the constant multiple rule. So minus 4.9 times, and then write down the derivative of t squared. And that's a job for the power rule. So 2 times t to the first power. And then clean this up a little bit. So it looks like minus 9.8 t. And this must be in meters per second, because h was in meters, and we differentiated with respect to t, which is in seconds. So the result is in meters per second.